Good evening, everyone. Here we are from Team ACS with session 2 on the topic Math Meets Future. So, before we dive into the topic, I should like to give a small intro about what we will be talking about this evening. So, the development of human race into a civilization would have been unthinkable of without the parallel development of mathematics also. Our ancestors used maths predominantly in the construction of many architectural wonders such as the temples in India or the pyramids of Egypt. With progress in times, as requirements to ease the burden of labor arose, man started inventing machines, the first of which was wheel. Once the standard of everyday life started improving, there was no looking back. When various predictions about the construct of the cosmos were being heatedly debated about, advancements in computational field was just underway. Now, in the 21st century, where with just the click of a finger we can have a look at different galaxies, the only thing of greatest uncertainty is the future. But the science of astrology, which was developed in early India, makes predictions about the future. But the extent to which these predictions are mathematically justified is of question, or we don't know enough mathematics to understand the science behind astrology. While we claim to be at the peak of technical advancement, there are many mysteries in the mathematical world that we are still ignorant of. Will we be able to understand the universe better when cosmological studies and computational advancements work together? Now, these are few questions that we will be attempting to answer in this webinar. With this, I give the stage to the presenter, Shyamana, and I welcome him. All the best. Good evening, all of you.
Good evening, guys, and I am Shyam. So that was one huge introduction. So I don't think that will be that formal as you can see. We'll start into the presentation. Jaga, is the presentation visible? Okay. So wait just a second, guys. I'll just confirm whether everything is okay. So good evening again. I am Shyam. You don't have to call me Anna. First of all, I'll just say once. So math meets future. We'll jump into the things which you're going to see now. I'll say something about the basic like there are many fields in mathematics and one of them is probability. So the basics of probability is the probability function. Probability function says about the likeliness of any event which can happen in future or which can happen now. So this probability function is P of A is defined as n of A by n of U. So what numerator says is like the number of favorable outcomes divided by number of all the outcomes combined. So this ratio will say like what is the percentage of the possibility or likeliness in which the event can occur. Since I said something about the basis of probability, let's play a game. What is the probability that you can win a game if you play right now? So it can be win or lose. So there are two outcomes, win or lose. So favorable is win. So win by win plus win, that is 1 by 2, that is 0.5. Now, if I say that the game is of picking cards out of some face down cards, still the probability stays 0.5 because I didn't say much rules about this game. Now, the same game, if I say that the probability, the winning condition is to pick out a spade ace out of the deck. So now what is the probability? You might have suddenly thought of 0.192 or something. So this number is basically 1 by 52, which is like 52 cards are there and one of the card is ace of spade. And so the taking ace of spade has probability of 1 by 52. So this probability suddenly dropped from 0.5 to such a low value. Now, in the same game, if I say that the deck is unshuffled, and unshuffled in the sense like when the deck is made, it will be in order, like from A to K and A to K, like that. It will have sets. So if it is that way, what is the probability for picking out ace of spades? It's still 1 by 52 because you don't know whether it is in the order or not. Listen carefully, like it is in the order, but you don't know. But when you know, then the probability becomes 0.5. You may ask, why not 1? Because you can choose whether you want to win or not. It doesn't mean that if you can win, you will win, right? So now you have the control. So it started from somewhere uncertain, and slowly with data, it became such a way that you can control the outcome. So this is some gist about seeing the future, or what is, I mean, to control what will happen in the next second or something. To do that, what was the difference? Like in all the scenarios, I said about 4 scenarios. What is the difference between them? The thing is data. So each had a different set of data. Like enough information was given only in the last point, so that the probability changed. So in this world, if you want to like predict what is going to happen next, like whether you will get a girlfriend or not, so all those things need data. Data in a sense, every data which humans have ever discovered and also are yet to discover. So first now, we'll see what are the datas we have right now, and start with physics. So physics is classified into 3: classical, relative, and quantum. So this classical physics starts with Sir Isaac Newton. So a famous figure who everyone knows him. So he said about gravity. He's most famous for the apple thing. And the main thing was he mathematically wrote the laws of motions. So, and also the universal laws of gravitations, with which pretty much we can almost predict the planetary motions and all those stuffs. And he also invented calculus. So this was supposed to be said first. Calculus is a mathematical tool which is very powerful, to model anything. What is modeling? Like, say, if there is something happening, say a drop of water is flowing from some height to some other height. To define that, we can say in words, right? So just the water is falling from there to here. Same way, we say that in numbers and equations and stuffs. So calculus is one heavy tool which helps us in that. What you see in the screen are, 3 things like in blue. This you might have learned in the schools, like I think 10th standard or 12th standard. So integration, differentiation, and limits. In the university, you might have encountered these red stuffs, which are like curl, divergence, cyclic integral, triple integral, partial differentiations. So all these things. So all of these combined will help us to frame equations for what is happening in the universe. And one such field where we frame equations is classical mechanics. Classical mechanics deals with everything like macroscopic levels, which is like specifically solids. They can be solid mechanics or solid dynamics. All those things will come under classical mechanics. And there is fluid mechanics. Fluid mechanics is slightly tougher than classical mechanics because the particles can have any random motion or stuff, so it's slightly more difficult. And there is things about turbulence, chaos theory, and all those things. So these two will define macroscopic quantities like the velocity, the pressure, and all those things will be defined by classical mechanics and fluid mechanics. Then there is optics. So we jump into something more interesting. So that is optics is study of electromagnetic waves, like how they interact with the surroundings and also how they go through a glass, all those things. Basically, there are 3 properties: reflection, refraction, and diffraction. Optics gave birth to cosmology and astrophysics. So how we, if we see from with our naked eyes, like it's not that we can see all the mega structures like nebula or superstars very clearly. So what we do is we use a telescope, and specifically we say radio telescope. Like radio telescope is slightly different from usual optical telescope. What it does is it gathers radio waves which are of higher frequency or even lower frequency than the visible spectrum. So this beautiful thing is the same from the before thing. So this is nebula of pillars of creation, a famous thing. You might have seen these pictures in NASA website or almost any other YouTube videos. So what you see in the right side is the most commonly known, but in fact, the right side picture is not true. The thing on the left side, the red color picture, is the true one. So, but it is less attractive, right? So the one in the right side has more clear definitions, and there are different colors and stuff. So how the picture on the left becomes the picture on the right? The thing is, when we use radioscope, we take different frequencies separately and we shift the frequency so that it is easy to analyze. Example, in the actual case, the sulfur and hydrogen are in the same red scale with some slightly different shade, and oxygen emits radiations in green scale. So these colors are not almost close to each other, so it is not easy for us to perceive like what is the quantity or how the concentration is in different regions. So we shift the frequency from one frequency to other frequency. Like hydrogen's frequency will be like moved from red to green, and same way oxygen will be moved from green to blue. This way the picture becomes more beautiful, and also it is more useful. Like people can understand hydrogen's content is this much, sulfur is this much, and oxygen is this much. And then the latest thing, a black hole. So it was captured in 2017, but it was released far later because of all the processing data things and stuffs. Black holes are very hard to detect. Why? Because they are black holes. They are very black, so we cannot see them. But how we know that this is a black hole? The accretion disk. What is accretion disk? When a black hole comes near a star, black hole has immense gravitational force eating the star, and the other star starts to die. And this star, when during its period of death, what happens is they go around the black hole and have a disk-like thing. So that disk is accretion disk, and we can see the disk because that disk is come by like basically the dead body of stars, and which we can see. It will emit radiations, and that's what we are seeing. So anything beyond event horizon will not be visible at all. So now there was another classical mechanics, that is waves. So waves usually of two different types. One is transverse wave and longitudinal wave. Transverse wave is for strings and kind. Longitudinal wave is when for sound and stuff in air mediums. But there is another guy who's a wave, but uh, who doesn't need a medium. Like usually normal waves will need a medium. Then there is light. So light is wave. It's an electromagnetic radiation which doesn't need a medium. It can go in space also. This light had brought many unsolvable stuffs which was later solved by the predecessors of the first scientists. Then electromagnetism is considering both electrical and magnetic field as one and the same, which defined the velocity of light. Like speed of light was constant, it was said by someone, and the velocity, I mean, the exact number was calculated by Clark Maxwell, and he, according to him, the speed of light was fixed for different medium. Like in a medium, it is constant. It's not like the velocity of light is same for air and same for water and same for space. In a medium, say it's a space means in space everywhere the speed of light is constant. And then everything about electricity all came from this field, and almost like the mobile phones and the laptop and all those things were developed from the theories and mathematical equations of electromagnetism. And then there is thermodynamics. So thermodynamics deals with cool and hot objects, and how the temperature flows and all those. And also it says about something called entropy. Entropy is measure of randomness. So I rushed through classical mechanics. So what is this? Like finally, all the components in classical mechanics tried to deal the whole universe as a clockwork, as if everything happens in a a chain or in a predictable manner. But then, can we really predict everything? So no, few things happened, and we got this. No, not him. I was kidding. Like he's John Wick. So actually, like there were many anomalies happening. So those anomalies were not, well defined using classical mechanics. Then we needed much more than just classical mechanics. Sir Albert Einstein, like a most famous figure, and he gave a relation between energy and mass, and he said like they are one and the same. So they are, if you have energy, they can be converted into mass, and mass can be converted into energy. So and he included speed of light also. So general relativity. First, I'll say what is relativity. No one can say something is fast or something is at rest. Everything is at rest or at motion with respect to something else. So we'll have an example. Like there are two trains moving in the same direction with velocity of 160 and 150 with respect to ground. Now, train A is moving only 10 kilometer per hour with respect to train B, because the other train is moving with the same, I mean, some velocity in the same direction. So it appears as if it is moving slower to this train, not as fast as the for a observer from the stationary point. So this difference in velocity does not happen for again one other guy. Is light. So that's where special relativity came from. I'll explain like why it is not applicable for light later. Then general relativity, generally it states like everything is made up of sheets, like space-time sheet, where all the three dimensions and also time are made of a membrane which is like stretchable, elongatable, and even we can puncture them in cases like black holes. So gravity, Newton said that gravity is a force. Einstein said that gravity is nothing but a curvature in the space-time itself. Like when there's mass and there is a heavy object that forms a curve in the structure, and anything which is going near the object will fall into the curve, and it will finally collide the object. So that's how in general relativity we see gravity. And not just that, even the space-time thing will stretch or elongate when you move faster. So why is that? We'll see why is that now. So time dilation, I'll explain with the most simplest example which you can see. Let's say there's a running race between a photon, that is light, and a human. So human is running at some say 340 meter per second, and the photon is moving at its specific constant velocity 29979 meter per second. So the guy who is seeing both of them running, he will notice that the photon is moving at this constant velocity, and also the other guy is moving at 340 meter per second. And but now the guy should be, I mean, the guy who is running, he should see the velocity of light is slightly lesser than what it should have been. But no, it is same for both the people. A guy is standing, other guy is running, but still the velocity is same. Like there is no difference in velocity of light for both of them. Either the velocity is not same, it is variable, or else something else is happening. But the equations which Maxwell gave were like more legit, and Einstein felt like maybe it is correct only. So what is the other thing which is changing? Time. So to compensate for the reduction in velocity, what happens is space time itself slows down for the person who is running. So the one who is running very fast, he'll experience time slowly. So for him, it will appear as if the light is going faster at the same speed which it happens for the person at rest. So to keep the light speed as constant for both of them, like space time curves or bends itself so that the time goes slower for one person and compared to the other. So this is like the major concepts of time travel and stuff. So this has been proved by many stuffs. We'll see them in quantum physics and stuff. So time, basically, in a summary, time slows down for the person who's running fast to make the light speed same for both of them, like the one who's standing and one who's running. And then the quantum physics. So quantum physics deals with something smaller, not that thing which you think. So say like humans dimension is around 1 meter, 1.8 meter, I think. So let's say 10 to the power of 0. It's in the order of 10 to the power of 0. And then, meters. So then we'll jump to atoms. So atoms will have a diameter of around Armstrong unit, so which is 10 to the power minus 10. In atoms, again, we have nucleus. So nucleus will be much smaller than the atom itself. So nucleus will have around a femtometer, which is like 10 to the power minus 15 meters length. Inside the nucleus, we have protons and neutrons, right? So that everyone knows, but inside even proton, we have something called quarks. So they will be much smaller than this, 10 to the power minus 10 meters, so theoretically. And is this the smallest? No, that is Planck's length. No, not this length. This is just Chuma Planck. That is what you will get if you Google Planck's length. So this is the actual value of Planck's length. This is the shortest length humans have theorized. What this length corresponds to, we'll see that in a while. So just for making sure that everyone is on the same page, 10 to the power minus 15 is 1,000 times bigger than 10 to the power minus 18. Yeah, deal with it. Next, how do we see things? Since we are going for smaller objects, how do we see? So first I'll define how we see itself normally. Light originates from a source and it hits an object and gets reflected, and we'll hit them with our retina and we'll feel them and we'll see them. So that's how seeing works. Light gets reflected and we see them. But for a particle of such small size, like say quark was 10 to the power minus 18, I think. So, but gamma rays, which is like highest frequency, like usually, so that is around 10 to the power minus 12 frequency. What happens is the wavelength itself will be like very high compared to the object size, so that it can easily not even touch the thing which we want to see, and it will go away. To see that properly, we have to reduce the wavelength further and further. Reduce the wavelength till at least when it is equal to that of the particle size. But when we reduce wavelength, we actually increase the frequency. So frequency increases means the energy increases. The light energy is so high that it can disturb the particle itself. So see what happens. By seeing, we are changing that. So it's like the quantum particle. For seeing, we are sending a light wave which is strong enough, and it is like shorter wavelength to see it. But at the same time, the particle itself get disturbs and it flies off. So this brought some uncertainty. So how do we do math without seeing? So since we are not able to see the things which are very small, so small, so we have probability again. So probability function. What is a probability function? Say a wave or something, and for an electron, we cannot exactly say where the electron is. So we'll represent it as a function where the amplitude of the wave, it says the probability that it can occur there, and the wavelength of the wave will tell us the momentum of the particle. So it's like if the amplitude is more at the center, for example, in this case, the electron is more likely to be in the center. It can be in the other sides also, because there is still probability of it to occur other sides, but predominantly it will occur in this middle, and its momentum is proportional to the wavelength of the wave. So that's how we mathematically define it. But the problem is superpositions. Like no, like if we are fixing the position of the particle, let's say, then the wave will become a pulse wave where the amplitude is high only at one point, right? So for a pulse wave, we cannot define wavelength at all. So it's like wavelength is a cycle, right? So there is no cycle in a pulse wave. So it is very hard to determine the wavelength. It is like it can be zero or it can be very high. So momentum is not determined when we say the position for sure. At the same time, if we say the momentum is constant, momentum means the wavelength is constant. At that time, the probability that the particle will occur at different places is same. So it can occur in the first loop, second loop, third loop. So it can equally occur in all the places. So if we say the momentum for sure, then we cannot say the position. So this is Heisenberg's uncertainty principle, where we say either we can find the position or we can find the momentum. We cannot do them together. So that's one issue. Talking about not able to do multiple things together, there is Schrodinger's cat's experiment, like famous experiment, mostly like everyone might have known already. So I'll explain once again in a short manner. So we have a cat, we keep a bomb near it, and we close the box. So the bomb has a probability that it can explode anytime. We don't know. Even if it explodes, the box won't blast away. So box is very solid. Imagine like that. Now, either after some time when I open it, the cat should be dead or it should be alive, right? So that's as simple as that. Since the probability that the bomb will blast is half, so it can be dead or alive. As per quantum physics, like when we mathematically define them, we say it is both dead and alive at the same time. This is kind of absurd. Like the cat is both dead and alive, and we have to do the equations and everything with assuming that it is both dead and alive at the same time until we see it. This idea itself, freaked out Schrödinger, and he switched it to biology after this. So there are many historical stuffs happened at the time. And then other quantum thing is other main part of the quantum mechanics is quantum entanglement. What happens in quantum entanglement is, see, when we create a particle, there is a property called spin. So for now, I'll just say like spin is rotation about its own axis, and if there is a particle with anticlockwise spin, automatically we have, there is a counter particle created along with it that has clockwise spin. So they both are one and the same, but still with different directions in spin. That's it. Now, when the particle is created like this, and if they go away, let's say after some lot of time, and it has a distance of 1,000 light years between them, Now one particle is near us, another particle is far away in the other part of the universe. So what we can do is, like, we can find the spin of one particle. Say if we find the particle which is near to us is anti-clockwise, we suddenly know that the other particle which went far away, right, it has clockwise. So before finding it, it is both clockwise and anti-clockwise, like how the Schrödinger cat was. It is both dead and alive, right? So same way it was both spinning in clockwise and anti-clockwise, but when we found that it is clockwise, the other thing was anti-clockwise. Or in the other case, if we find this is anti-clockwise, the other thing will be clockwise. So this sudden, even though the other particle was light years away, we are able to know the information about it, right? So it's as if the information traveled faster than light. So this is gist of quantum entanglement. I'm not going in deep into the mathematics. Just I'm saying what it is. So I don't think it is really useful. The outcome of clockwise or anti-clockwise is totally random. So this may not be useful for sending information or getting information or communication for that matter. So then there is other things, like when I said, right, proton is made up of quarks, even neutron is made up of quarks. So we have all the elementary particles which cannot be further divided into smaller particles. You'll see the green parts are leptons. Leptons in the sense they are like electrons, and the other one next to the electron is muon. It is a bigger version of electron, fatter version, let's say fat cousin. And tau is another fat cousin who is suicidal also. So the lifetime of muon and tau is far less than electron. Electron can stay for a long time in the same thing, but muon and tau will disintegrate, or even sometimes change into electrons. So all these things will happen. But electron, since it is stable, like we are able to see them abundant in the universe. So in the first column, the first three, the up quark, down quark, and the electron, these are the things which we see most commonly. I'll show you once. So say proton is made of up quark, like two up quarks and one down quark. If you notice properly, here we have charge in the equations, like in the diagram. So up quark has plus 2 by 3 electron volt, and down quark has minus 1 by 3 electron volt. So when you do the math, it adds up to 1. So proton will have positive 1 electron volt, and at the same time electron will have negative 1 electron volt. Same way, if the structure is replaced by one down quark instead of an up quark, it becomes a neutron. So one up quark, two down quarks. I'll say again, the quarks makes proton and neutron. And if up down is combined, it becomes a proton. If up down is combined, it becomes a neutron. So again, the charge is like balanced, right? So it is zero. Neutron is essentially neutral; it doesn't have charge, but the quarks which are inside the neutron will have charge. And how they are combined together, something has to fix them together, right? So that fixing is done by gluons. Gluon, the name suggested, is a glue kind of thing. So gluons are responsible for strong nuclear forces. The gauge bosons, or like gluon, photon, Edison boson, and W boson, all these things are force particles. So gluon corresponds to strong nuclear force which binds the nucleus together, and photon corresponds to light or electromagnetic wave. And Z and W boson are very interesting. They are for weak nuclear force. Weak nuclear force did a lot of stuff in quantum world. Like weak nuclear force is the only thing which have partiality between clockwise spinning and anti-clockwise spinning matters. So it behaves differently based on the spin. Any other force, or let's say gravity, or even all the things, electromagnetic wave and everything, they see a particle is spinning clockwise and particle is spinning anti-clockwise is one and the same. But the bosons, the Z boson and W boson, the weak nuclear force will not see them as the same thing. It will deal them differently. So these details about this will be available in the next session on next Friday. So for now, I'll just go through what are the things which I have invented. And that is Higgs boson. Higgs boson is far more interesting. That it is almost like air molecules, like currently right now. We have a lot of air and we are inside the air. So what happens is whichever reacts with Higgs now, like Higgs field is everywhere. So everywhere we have Higgs energy, and whenever any object or any quark disturbs this Higgs field, it has mass. So it's something interesting. Not just any force, it has mass. Anything which doesn't disturb the Higgs field will have no mass. So photon and gluon won't disturb the Higgs field, so they don't have mass. And everything else, like the up quark and down quark, they have mass. So up quark and down quark are there in proton and neutron, so which is very famous. But where this charm, top, strange, and bottom came from? So to know about them, there are two sources. One is naturally occurring phenomena. There's star, specifically neutron star, or any even explosion time supernovas and stuff. And there is LHC, Large Hadron Collider. What? Okay, LHC, I'll say what it is. Large Hadron Collider. Hadron is nothing but a combination of quarks in either three in one pair or two. So say it can be like a proton also. Even proton is a large hadron. So what they do is they accelerate it to very high speeds, like close to speed of light, and they collide them together, and they break the thing. The proton gets broken, and the up quark and down quark will scatter outside, and even there are other particles which will be like created because of this collision. So the large hadron collider will help us to see different kind of quarks which evolve, or which we are able to measure some parameters about. So I said about stars, right? Naturally occurring phenomena for other quarks. So how star functions? I just say a summary. Nebula is a gas cloud. Say simple. In space, we have a lot of ions and stuff. So hydrogen ions and oxygen ions and all those. So because of gravity, they start coming together. When they come together, when the mass is increasing, what happens is the pressure and temperature at the center will be very high, and that pressure and temperature will induce nuclear fusion. Nuclear fusion is a reaction where small lighter nuclear join together to form a heavier nuclear. For example, hydrogen will join together to form helium. So the principle is slightly more stepwise, not just directly. It will not come to helium, but that's how elements are formed. Say maybe everything was just hydrogen at the starting, but because of stars and this nuclear fusion, all the other particles are created. So from hydrogen to iron, the nuclear fusion occurs, and iron is the last thing because iron has stable nucleus. So after that, the nuclear fusion stops for some reason. Okay, the reason is apparent because iron is more stable than anything else which is going to come after that. When the nuclear fusion occurs, the radiation from the inside will push everything outside. So it's like the heat and the light which is coming from the center of the star will push the outer surface of the star to some distance, which will be balanced by gravity. Gravity will be trying to pull everything inside. So this force balance will stop when the fusion stops. So the gravity will win, and it will be compressed to very small part, and sudden compression will lead to explosion. So that explosion is called either supernova or hypernova based on the size of the star. And in the result, if the after the explosion it won't stop, it will be like a step explosions. Like once it explodes, it comes back again and again it explodes. So it happens like that. And when it comes back and compresses, right, so at that time, if the radius of the star which comes back is smaller than the Schwarzschild's radius. Schwarzschild's radius is defined for some particular mass. Say for our sun, the Schwarzschild's radius will be around some um, a meter or so. I'm not sure. So what happens is within, if the whole mass is compressed lesser than that Schwarzschild radius, it will become a black hole. Or if it is not, like if the radius is more than the Schwarzschild's radius, it will become neutron star. What happens in neutron star is proton and electron will combine together. Proton was positive and electron was negative. So when they combine, it will become again another neutron. So everything in the whole neutron star will become a neutron. And in the core, strange things happen. So the core will have even further higher pressures where all these things like the gluon will break, and each quark will start transforming into something else, and that is one theoretical source of strange quark. So don't worry if you didn't get much about the quarks and stuff. Like in the next Friday, it will be explained very clearly by two experts. So then quantum gravitation. So this is where everything falls. Gravity was not as easy to deal with in the quantum world. I mean, in a smaller scale as it is in the outer scales. I mean, in the classical things or in the relativity. So what people did is to bring mathematically the concept of gravity into the quantum world. They proposed a particle, graviton, but this particle didn't really help us solve the equations. It broke down all the equations. Then to solve this, the string theory came. So what is string theory? String theory says like every quark or every leptons or even Higgs bosons are made up of strings which has its own mode shape. Like see here we have different shapes, right? It's same as guitar strings which will produce different sounds based on its tension or something. So each thing will be like made of the same string, and depends on the mode shape it will exhibit the properties of some particular elementary particle. So that is string theory, and it included gravity also, because when it became strings, like the equations was like huge, and it needed 10 dimensions to solve. It's not like matrix, it's 10 dimensions in the sense like there were only four known dimensions in the time when classical physics was there. So those four dimensions are x, y, z, and the time. So we see what are the 10 dimensions are required to string theory. Like there are many proposals for the 10 dimensions. So x, y, z, and time are common. The first four is over. Now say today morning, if you are planning to whether wear a red shirt or a green shirt, that's a decision point, right? So that is a point, we say decision point. So from the decision point, if you either wear a green shirt, that starts a new reality where in that everything happens which will happen after we wear a green shirt. If you are wearing a red shirt, then that has another reality. So it's like a single decision point will create two different realities. So that's one source of like the next dimension. So fifth dimension is stated as the ability to move between different world, where instead of green dress you wore a red dress. So it's like that's a same decision point, but the decision which you took is different. Or not just you, it can be like Schrodinger's cat. If it is dead, it is one universe. If it is alive, it is another universe. So it is both dead and alive at the same time. So it, when we get to know, it will start two new universes. So the ability to move from one universe where one decision happened to other universe is fifth dimension. And then the sixth dimension, it states that we can travel in time like front and back in the parallel universe where it had the same decision point. Then what if the decision point was itself not there? For example, like we say Schrodinger's cat, and if the decision point is where you have to decide, right, whether you have to do one thing or the other. If that decision point is not common, then that is seventh dimension. Like we are able to move from one dimension with another dimension with a completely different decision point. And again, the eighth is time traveling in such dimensions. And ninth is like being able to see all the laws of physics and Big Bang itself from different initial origins. So the whole Big Bang starting to ending, it has laws of physics and all those things. It has expanded. We don't know what is the end till now. So from the start, everything which we saw, that will become a single point. Like a single dot will have all the information started from Big Bang to the end of the Big Bang. Same way we have lots of dots. So all these dots can be like shift like one dot to other dot. So it's like being able to see one Big Bang and again being able to see other Big Bang. So that's nine dimensions. So slightly mind blogging. And there is 10. To be frank, 10 is like everything possible, which is slightly even beyond the human abilities to understand. So yeah, I can confidently say that I don't understand what is 10th dimension. But so these 10 dimensions are there with further much more complicated way of weaving the universe itself. What if there was someone who with consciousness, with the ability to of nine dimensions or so, where he can go to future or past anywhere, or he can change the realities, all those things. So I think that is pretty much close to the definition of God, right? So and it can be done. I mean, anything can be done if he wishes to. So nine dimension beings, let's say it's a god. um, he looks something like this, I hope. So not necessarily like this, but you understand, right? So this is something which is tough to realize, but it's how it is. So to solve string theory, we have to solve with all the 10 dimensions, and finally, after we solve with 10 dimensions, we'll remove the unwanted dimensions, and we'll have the four dimensions, which is for the real world. This string theory, since it connects the gravity and the quantum realm, so this together will join all the parts of physics, like the classical, the relative physics, and the quantum physics. All these are combined together. So when we combine different parts of physics into some single same theory, so that becomes theory of everything. But unfortunately, till now, there are no experimental results or any proofs for string theory. So this is how it is. So string theory is one proposal for theory of everything. There are other theories also. If only understands the string. Okay, so this is one set of data. We'll come back to the purpose of this presentation. What I was saying is we need data to predict the future, right? So that is one set. Same way there is a ton of sets for biology, psychology, chemistry, and so many other stuff which even I don't know. So all these data sets, whichever humanity has found, can be combined, and will it still be enough to find the future? No, it doesn't look like it, because there are still lots of loopholes and gaps which humans have not found, and also there are many things which we don't even know that we don't know. So all these things are there. So, but what if I don't even have this much data? Let's say if it was like 5,000 years ago, I don't have any instruments, or I don't have any communication device or anything, so I don't know many things. So if I'm interested in trying to predict the future, what would I have done without any data with me? Statistics. So yeah, we'll see what the statistics is like. What we do basically, statistics, see, whatever is happening around, it can either be totally random, or it can also be something which is like structured by someone who's from higher dimension, let's say 11th dimension. So it is even beyond 10. So but what happens is, if suppose by chance, if everything is designed by a constant thing, we can find patterns, right? So by finding patterns, we can do something, or let's hope that we can do something. So also nature shows many patterns. For example, not just in humans, there are many things will repeat itself, so all those things will happen. So nature shows a lot of patterns. So sometimes statistics, what we do is we just gather results ignoring the cause of the results. So whatever it is, we'll just see like what is happening around for every people individually, and we'll try to correlate them somehow. So correlation in the sense connecting the results of each individual person. Let's say, for example, there is a place, and if someone goes to that place in April, he dies in the next 5 years. Let's say this happens for 4 out of 10 people. So say I am analyzing only 10 people, and 4 of them died in 5 years. So I slightly get a fear of not going there. So this fear, right? So this fear is going to stop me from going there. So this came because of statistics. I did the statistics and I found that it is bad. Or something more silly. Say on the full moon day, if someone is wearing yellow dress, suddenly he gets something happy in life. So if it happens for like say 6 people out of 10, maybe I'll wear yellow t-shirt. Like what's the wrong in doing something just if it is what if it was already a plan by someone else? So since I don't have data, not like the current world, we are still in the 5,000 years old past. So for correlating not just this place and date, we can have stars, right? Stars look beautiful, they are far away, and I don't know how, but people see shapes in them. So apparently, this triangle and stuff are of specific animal shapes or specific stuffs. So what I can say is, okay, starology. Why I named it starology? Because stars can also be called as astros. So it's copyrighted. I cannot use that astrology word. So I am theoretically producing a new thing which is completely new using statistics, and I name it starology. So what happens is, if I say like someone born in this star has to do something, something, something. So you get my point, right? So what is the whole point of starology is to get statistics and bring them in such a way that sometimes it may work, sometimes it may fail. But the thing is that astrology is some attempt or a social experiment. Hmm. Is it reliable? No, it is not. So when I started explaining about the statistics, some might have thought like, okay, this fellow supports astrology, something is wrong in his brain. No, nothing is wrong in my brain. I don't support astrology. Okay, so the thing is, most of them could be just luck. It could be statistics. Someone in the past who was very intelligent, say IQ of 270, but he was not able to see other things because of the lack of resource. So what he did, he might have gone for statistics, and he might have created this whole thing where he correlates every event with respect to that, like stars. It also made people happy, right? So if someone says that today is your lucky day, then who will not be happy? Say someone says like tomorrow is going to be a happy day for you, you'll be happy. But also there are backsides also. If someone says that tomorrow is a bad day for you, it is sad. So all these things are like together. And on a conclusion thing, this could have been a social experiment, just random statistics, and someone might have proposed this, and everyone might have thought like, oh, nice, nice, so I'll follow this, and most of them might have got results luckily. And what happens is those people who got the positive results, they will say like this is true, and those who didn't get the results now, they will feel like maybe it's not true, but they will get convinced by the people who got correctly. They will say like, because you didn't believe in it, so you have to believe in it to get it. So it goes that way. And what happens is this becomes a culture, and everyone, almost like many people, like predominantly majority of the people, will start following this. If I had created this 5,000 years ago, and people can misuse it also for money and other nasty stuffs. So what I'm saying is, to find the future, the best way is to get the data, learn, explore, find information, connect everything, create a theory of everything. So that is the best way to exactly say what is going to happen in the future. So nothing else is as close as that. Statistics, okay, it's fun, it's an experiment, but it doesn't work, guys. It doesn't work. It's just a gadget. So thank you. Okay, also, if anyone has any doubts, you can send them in comments. I can see the comments. Since it is a live show, I'll try to explain them. Hi guys. Also, catch up to the next series. Like in the next week, there will be a lot of stuff about quantum mechanics, and after that, there will be something about matters and antimatters. So it will be interesting. Like some things which you might have not got in this current presentation, you will get it in the next. And if there is any thing which you want to talk, you can comment in the live comments, or else I'll close this session in 2 minutes. Okay, guys. So I think something is wrong. Okay. Chat game.